Hi, and welcome to today's lesson. We'll be talking about orbital electronic configuration today. So at the end of the lesson, it is expected that you should be able to define what orbitals are, differentiate between shells and orbitals, explain how electrons fill orbitals using charts, Hund's rule, Pauli Exclusion Principle, and the Aufbau Principle. You should be able to write the electronic configuration of the first 20 elements using the periodic table. So basically, this is what we'll be focusing on in this lesson. So what's an orbital? An orbital is a region of space around the nucleus of an atom where there is a high probability of finding an electron. So they show us where the paths of electron around the nucleus, where electrons can be found. There are different types of orbitals. There is the s orbital. It is usually spherical in shape. There is the p orbital. It is dumbbell, as you can see on your screen. And then there is the d orbital, and then the f orbitals, having more complex structures than the s and p orbital. Okay, let's really talk about shells, subshells, relationships with orbitals. Shells represent energy levels in the atom. There are levels within which electrons occupy based on their energy. So the higher you go away from the nucleus, the higher the energy level of that shell. Okay, subshells are otherwise called sub-energy levels. They exist within shells. They exist within the main energy levels, and then they are called SPDF. They are also called orbital. SPDF also used to represent orbitals, as we will soon explain. Orbitals contain each subshell contains one or two orbitals, so more or less like subdivisions of subshells. Orbitals are more or less like subdivisions of subshells, and then although they are properly defined as the region where there is high probability of finding an electron, these regions are found within subshells. That's what we are saying. And then each orbital can hold a maximum of 2 electrons. Take note. So when a subshell has only one orbital, it means that that subshell can hold only 2 electrons. When a subshell has 3 orbitals, for example, it means that that subshell can hold 6 electrons, as we will soon see. Okay, for example, in the first shell, there is only one subshell, and then it has only one orbital. So it means the s subshell, or sometimes we call it the s orbital, can hold 2 electrons. In the second shell, there are 2 subshells, the 2s and the 2p. Take note, the energy level is used to denote the subshell for ease of reference, to differentiate it from another subshell in another energy level. So the 2s here means that the s subshell in the second energy level, and then the 2p here means the p subshell in the second energy level. So the s subshell has only one orbital, but the p subshell has 3 orbitals. So that means in the second energy level, there are 4 orbitals in all, one from the S subshell, and one from the P subshell. And 3 from the P subshell. In the third energy level, there are 3 subshells: 3s, 3p, 3d. So as we've said before, the S subshell only has 1 orbital. The P subshell has 3 orbitals, and the D subshell has 5 orbitals. So making them 9 orbitals in all. So if an orbital can hold a maximum of 2 electrons, what is the maximum number of electrons you expect to see in the third energy level? So if there are 9 orbitals in all, and each can hold a maximum of 2 electrons, it means the maximum number of electrons you expect to see in the third energy level is 18. So take note. So this can hold 2, this can hold a maximum of 6, and then this can hold a maximum of 10. So and then in the fourth energy level, there are 4 subshells: 4s, 4p, 4d, and 4f. And then the first, which is the S or subshell or S orbital, can hold a maximum of 2 because it has 1. The second, which is P subshell, can hold a maximum of 6 because it is 3 orbitals. And then the third, which is the D subshell, can hold a maximum of 10, which is because it is 5 orbitals. And then the last of all, which is the F, can hold a maximum of 14 electrons because it has 7 orbitals. So take note, this will be used subsequently in the orbital electronic configuration that we'll be going into shortly. So but before we configure an atom, before we distribute electrons within an atom, it is expedient that we understand the principles that guide electronic distribution within an atom. One of the first principles we'll be looking at is the Aufbau Principle. So electrons do not just fill an atom randomly. They fill in a particular order from the lowest energy level to the highest energy level. So this is how the energy levels are distributed in an atom. 1s has the lowest energy level. The next energy level is the 2s and the 2p and all that. So electrons are distributed into these energy levels according from the lowest to the highest. That's what the Aufbau principle is stating. So how would you remember these energy levels? You can use this chart. It's basically can be done by anybody. First is to write all the S subshells in an atom accordingly from 1 to 8. So there are S subshells from 1 to 8 energy levels, and then the P subshell starts from 2 and then ends in 7 in the 7th energy level. So we are from 2p to 7p, and then this D subshell starts from the 3rd energy level and then terminates in the 6th energy level. So 3 to 6, and then the F subshell starts from 4 and ends in 5. So in each case, it increases, where it starts increases by 1, and then where it stops decreases by 1. So it is easy for you to always write them out vertically. So you start from 2 here, ends in 7, start from 3 here, ends in 6, start from 4, ends in 5. So it increases by 1 in each case, and decreases where it stops decreases by 1 of the previous one. So and then how would you come out with the energy level distribution? So you just draw an arrow starting from the 1s to the 2s to the 2p, 3s in this form, in this order, until you reach the 8s. So that means the 1s is the lowest energy level, followed by the 2s, followed by the 2p, 3s is next, and then 3p is next, 4s is next, and then 3d is next, 4p, 5s. And then once you write them out in that order, you will be writing the energy levels in the atom from the lowest energy to the highest energy. So let's see if from what we've done so far you can test yourself and see if you can answer these questions. I would advise you pause the video and then see if you can answer the questions before we begin to discuss the answers. Okay, answers. The first question says, how many subshells are there in the n equal to 3 shell? And then how many orbitals are there in the 3p subshell? There are 3 subshells in the n equal to 3 shell. That's the 3s, the 3p, and then the 3d. Remember, when n equal to 3, there are 3 subshells. When n is equal to 1, there is 1 subshell, which is the 1s. When it's equal to 2, there are 2 subshells, which is the 2s and the 2p. As you can see here, just brought back what we've done before. The next question is, what is the maximum number of electrons that can occupy the n equal to 2 shell? So on the n equal to 2 shell has the 2s orbital and then the 2p orbital. Remember, each orbital can take 2 electrons. There's one s subshell, and then there is 3p, 3 yes p subshells. I take that again. There is 1 orbital in the s subshell, and then there are 3 orbitals in the p subshell in the second energy level, and everywhere for that matter. So all in all, we have 4 orbitals. An orbital can take 2 electrons. So in all, in the second energy level, where n is equal to 2, we have 8 electrons. So hope you got that. Okay, fine. Which orbital is filled first, 3d or 4s? So from the chart we have here, if you follow the chart and then it tells you how the Aufbau Principle defines the energy level. So if you go this way, the 1s comes first, followed by 2s, the next is 2p, followed by 3s, the next is 3p, followed by 4s, the next is 3d. 3d comes first. 3d comes after 4s. So it means that once you are filling the electrons in an atom, you fill in the electrons in the 4s subshell or orbital before you fill the 3d, because the 4s is at a lower energy level than the 3d. And then according to the Aufbau Principle, electrons occupy lower energy levels before they occupy higher energy levels. So basically that's what we are saying here. Okay, how many electrons can a single p orbital hold? Any orbital, one orbital can hold 2 electrons. The reason why p can hold 6 electrons is because there are 3 orbitals, so each is holding 2 electrons. So in all, the p orbital can hold 6, but a single p orbital can hold just 2 electrons. How many electrons can the 3d subshell hold? The 3d subshell as a whole has 5 orbitals. So the d subshell anywhere has 5 orbitals. So each orbital can hold 2 electrons, and then in all they can hold 10 electrons. So let's talk about the electronic configuration proper. Electronic configuration, just like I've said before, tells us how electrons are arranged within an atom. Electrons are arranged in atoms in a particularly defined manner. So in the orbital notation, uses subshell symbol with a superscript to show the number of electrons. For example, if you are 1s2 shows that this subshell or this orbital is in the first energy level, and there are 2 electrons that have been added to it. There are 2 electrons in it. And then 2p4 means that this subshell is in the second energy level, and then there are 4 electrons in all. Remember, the p subshell has 3 orbitals, so 4 electrons will be distributed among those 3 orbitals. That's what it means. And they can hold a maximum of 6 in all. So for the hydrogen atom has 1 electron in the ground state. So it's written, the electronic configuration is 1s1 if you are going by the Aufbau Principle. So electrons will fill the first energy level, which is 1s, before they fill the subsequent energy level. So 1s1, 1s1 because hydrogen has only 1 electron, so it will just fill the s orbital or the s subshell in the first energy level. And then for helium, it has 2 electrons. It will be 1s2. It cannot fill subsequent energy levels because the number of electrons are just 2, so they will just fill the first energy level and the first subshell. Lithium has 3 electrons, 1s2 and then 2s1. So the first subshell and the first energy level has been filled, and then the next subshell is in the second energy level, 2s1, as you can see. Okay, let's see other elements among the first 20 elements. Aluminium is number 13. That means it has 13 electrons, number 13 in the periodic table. It means it has 13 electrons in the ground state if it hasn't lost any electrons. So let me walk you through the configuration. So following the energy level, the first is the 1s. So 1s is written first. It has 13, so 2 electrons will go into the first subshell, 1s2. The 2 electrons will be given to the second subshell, 2s2, and the energy level is 2p. 2p can take 6, 2p6. So count 2 plus 2 plus 6, 10. It's 10 in all. Remember, there are 13 electrons. So the next energy level is 3s. So you write 3s2. So that's 12 in all. And then the next energy level is 3p1 because at this point there will be only 1 electron left. So if you just occupy the remaining p subshell. The next is silicon. Silicon has 14 electrons. It's number 14 in the periodic table. 1s2, following the energy levels. 2s2 because 2s is the next energy level, and then 2p6, 2p is the next energy level. So all in all there are 10 electrons. And remember, silicon has 14 electrons. So the next energy level after the 2p is 3s2, and then because s can take no more than 2 electrons, the next is 3p2. So 3p2 because there are 14 electrons. After the 3x, 12 electrons has been used, so remaining just 2 electrons. So the 2 electrons will occupy the p subshell. So the next is phosphorus. Phosphorus has 15 electrons. Following the energy levels, it will be 1s2, 2s2, 2p6, 3s2. At this point, 10 electrons has been used. The next energy level is 3p, and then at this point 12 electrons have been used. The next energy level is 3p, so that means 3 electrons will be left. That is why it is written as 3p3. So as you are filling in the electrons in each energy level, count them, and then that will tell you how many electrons are left. because you cannot an atom will not have more electrons in its shells more than it has. So there will not be more electrons in the shells more than the atom has normally. So it is necessary that you count whenever you are filling. So for sulfur, if it will be 1s2, 2s2, 2p6, 3s2, and then 3p4. So and then and so on and so forth. So let's see if you are conversant with what we've done so far. So pause the video and try to identify, or rather answer these questions, and then replay for corrections. Okay, I think you should have done that, and I hope you got them correctly. So the first is, an element has the electronic configuration of this. Identify the element. So basically, the number of electrons will tell you the number of protons, and then the number of protons in an atom is the atomic number. It gives you the identity of the element. So especially when the element has not lost any electrons yet. So if this element has not lost any electrons, all we need to do is just to add all the electrons, as that is the number in the superscript, and then at the end of the day we'll get the number of electrons. That will tell us the number of protons as well, and then that will be used to identify the element. So when we add, we get 35. So which means that and the element occupying the number 35 is bromine. So the 1s has 1s2 has 2 electrons, 2s2 has 2 electrons, 2p6, as you can see, has 6 electrons, and then 3s2 has 2 electrons, and so on and so forth. Just add them, and then that answers the question. Okay, an element has an electronic configuration of AR in bracket 4s1 3d5. Identify the element. So how do we identify the element? First, whenever you see electronic configuration written like this, AR in bracket means that this is the electronic configuration of argon. So you first write out the electronic configuration of argon, and then before you complete it with what is left. So if you do that correctly, you see that this is the configuration of argon. There are 18 electrons in all, and then the next is 4s1. 4s1 has 1 electron, followed by 3d5. 3d5 has 5 electrons. So once you add all, you get 24 electrons, and then that represents the element chromium once you check your periodic table. Okay, fine. Write the electronic configuration of the first 20 elements in the periodic table. These are the first 20 elements and their electronic configuration. Based on what we've done, I would advise you study them very well, and so that you can gain more insight. So I might not be explaining any longer because we've done the explanation already. Just go through and then practice on your own, and then if you have any question, you can let me know in the comment section. Okay, the next concept is the next principle that defines electronic configuration, or how electrons are distributed within an atom, is Hund's rule of maximum multiplicity. According to this rule, within a subshell, electrons individually occupy each orbital before they pair up in one orbital. Single electrons in the same subshell have the same spin. So remember, electrons spin basically revolve or move around the atom. So they can revolve in one direction or revolve or spin in another direction. So that's what we are saying. For example, this is how we represent the orbital diagram. Okay, before I go into this diagram, I'll just explain the Pauli Exclusion Principle. It states that no two electrons in an atom can have the same set of 4 quantum numbers. This means that there's a maximum number of 2 electrons in an orbital, and they must have opposite spins. And this is what we are talking about. First, this is how we represent orbital diagrams when we are writing electronic configuration. So if an element has an electronic configuration of 1s2, 2s2, and 2p2 carbon, for example, it means the 1s subshell is presented this way, and then one electron spins up and the other spins down. Both cannot spin in the same direction according to Pauli Exclusion Principle. And then this in the 2s, where we have only one orbital, one spins up and one spins down. So when you are drawing the electron, you draw an arrow facing up and an arrow facing down, because there are 2 electrons here and there are 2 electrons here. Now the 2p subshell has 3 orbitals, so you draw 3 orbitals. And then according to the Hund's rule of maximum multiplicity, electrons occupy singly, so you don't put 2 electrons in one orbital. So one electron will occupy this, another electron will occupy this. Before electrons would begin to spin in the opposite direction, all will spin in the same we have electrons spinning in one direction until we have 3 electrons spinning in one direction before they begin to pair up, and then once they pair up, the other electron spins in the opposite direction. As so it is either this way or this way. You can use this convention. You can spin in this opposite. The opposite direction can be in this way. So but not this way. So you cannot have one spinning in this direction and one spinning in the opposite direction. No, they all occupy singly with the same spins before pairing up takes place. And then this is also wrong. According to the rule, electrons occupy singly before pairing takes place. I say once they occupy singly, they point towards the same direction, they spin towards the same direction. That is what it means. So take note. You could practice them for other elements. Okay. This is boron. This is the orbital structure for boron. The first will have the 2 electrons spinning in different direction. Second will have spinning in different direction, but the third will have only 1 electron spinning in one direction, because boron is 1s2, 2s2, 2p1. It has 5 electrons. So this is the orbital diagram. And then okay, and then the next is carbon. Okay, we'll discuss carbon. This is also possible for carbon, and then this is possible for carbon as well. So take note. You can also when the atom is excited, the electrons can be promoted to the next empty orbital. Okay, for nitrogen, where we have 7 electrons, the electronic configuration is 1s2, 2s2, 2p3. This is how the orbital diagram will look like. So 2 electrons with opposite spins here, 2 electrons with opposite spins here, and then electrons occupying singly with spins in the same direction. And then oxygen, 8 electrons. This is the electronic configuration. 2 electrons with opposite spins, 2 electrons with opposite spins, 3 electrons pointing in the same direction, and 1 pointing in the opposite direction as they pair up. So take note, that is very important. So the orbital diagram for some atoms are shown. Some are correct and some are wrong. I will let you figure that out. Which do you think is correct, and then which do you think is wrong, and why? Okay. This is a task I would want you to do. If you have any concerns, remember to let me know in the comment section, and draw the shapes of the s and p orbitals. We've done this. You could refer, you could go back and then see them, or use internet resources just for practice sake. how many orbitals are in the 4D subshell, write the electronic configuration of the 21st to 30th element, why does copper atomic number 29 have an electronic configuration of this instead of this. So yes, little research will do, and then this as well for practice sake. I will not be answering them. Like I said, if you have any concerns, let me know. Thank you.